Okay, so as we continue on here, class with 9.2, there's a little video I want to show you here. It's just kind of for fun. We talked about the phases of the moon and how the moon revolves around the Earth, right? We talked about this and what the phases look like as the moon goes around the Earth. We see different phases of the sun. So this one's just kind of a little fun video. What if the moon were replaced? And let me just double check here. This is by Yeti Dynamics. Pretty good videos. Whoops. What am I doing? Play. Okay. So this one, what if the moon were replaced with some of our planets? So just looking at the size of the moon versus the size of the planets, what our horizon might actually look like if the moon were replaced. Now here's the moon. Okay, that's the size of the moon there. That's exiting. What if we had, oh, what's that one? Oh, that's Mars. What if Mars was in the same position as the moon, if it was close to Earth and it was revolving around, or that's what it would look like in the sky. Oh, what's this one? Venus. Okay, so if Venus were in the moon's position, that's what we would see in the sky. Oh, which one's this, do you think? Neptune. Okay, so Neptune. That's pretty big. That's pretty big. Now, we'd have all sorts of problems if we had something large like this near to the Earth. Uranus, yes, it looks very much like Neptune. What's coming next here? Whoa. Jupiter. Can you imagine? Yeah, it's Jupiter with the stripes and the storm and everything. That's good. Yeah, Jupiter. Yes, this would not be a good situation. Right. Yes, we would collide. This would not be, yeah. Well, you know, yeah. This is not realistic. This is just sort of like, oh no, this is my favorite right here. Wouldn't that be cool to see that every day? Oh, look at it. And its moons would be real. Yeah. No, this is not realistic at all, but yeah, if this actually happens, you would have to wake up from your dream. Yeah, anyways, cool. Okay, so there you go. It would be nice if we woke up to Saturn every morning. I think that would be pretty cool. But Earth would be very different. The moon has a lot to do with tides and with, there's all sorts. Saturn's pretty big. So that wouldn't work all that well. But just for fun, what if the moon were... Okay, let's continue on. Your notes should be in front of you there. You should have some blanks to fill in as we talk about eclipses next. This is still part of 9.2 in Pearson's Saskatchewan Science 9. Your textbook, you can follow along here. But we talk about eclipses here today. The Earth revolves around the sun. We know this. And the moon around the Earth. Sometimes there is a shadow that is cast if the Earth and the moon line up with the sun. So eclipses are different than the phases of the moon. That was brought up earlier. Eclipses are a little bit different. The phases of the moon, again, we're just seeing the sunlight on the moon in different ways, right? Depending on the position of the sun and the moon. So what happens if either the Earth gets in the way of the sunlight towards the moon, or the moon gets in the way of the sunlight to the Earth? So here's the first, okay? So this is an eclipse right here. And so here's our sun. And again, this is not to scale or anything, but this is the sun super far away. So what happens if the moon happens to be right in between the Earth and the sun? Well, what happens is we get a shadow that is cast on the Earth. Now, we won't get too far into this really per se, because there is this little spot right here. You see that little spot that's kind of on Africa there right now? Okay, so there would be a full solar eclipse, okay, if the sun was blocked out by the moon. If you were right here, living right here, okay, that would be a full eclipse. But if you were living over here, okay, let's say, you would be able to see, part of the sun. Only part of the sun would be covered, okay? And again, there's different, there's partial eclipses, total eclipses, and that sort of thing. Okay, so this would be another picture, I guess, right here, right? Yeah, that would be what it would look like if the moon was directly in front of the sun.
Why can't we look at it?
Well, you don't want to look at the sun because of all the radiation, right? Now, to look at eclipses, if you have partial eclipses, your eyes are not really meant to look directly at the sun for any length of period. If you have an eclipse like this, there's still some radiation that's coming, still some really bright light that would sneak around here. So yeah, even if you have any kind of eclipse, you should have proper protection to look at those. Some would say you shouldn't even look at them at all, even with proper protection. But anyways, what did we have? We had a solar eclipse not too long ago here, partial, but a couple years ago, and the moon was partly in front of the sun. The sun was partly blocked out, so it's kind of cool. And this is what a total eclipse would look like. Okay, now that's a solar eclipse, right? If the sun is blocked out, it's an eclipse of the sun. That's solar eclipse. A lunar eclipse is when the moon is covered. Now, what would the moon be covered by? Well, it would be literally the shadow that's cast by the Earth. So if the Earth is right between the sun and the moon, and again, this is not easy to do. This doesn't happen very often at all, because the moon is, you have to understand, the moon's pretty small. The Earth's shadow is pretty small compared to just, space. And so for the moon to actually be in the Earth's shadow, it doesn't happen very often at all. But this is sort of what it would look like as the Earth sort of passes in front of the moon, or the moon kind of, is moving around the Earth as well, and the shadow might be passing. So as more of the sunlight gets filtered through our atmosphere, some of the colors of the light get filtered out. So that's why the moon actually could look, in an eclipse, could look a different color. Could look yellow or even red or things like that. Because the atmosphere of the Earth, and you have to remember that around the actual rocky Earth planet, there's an atmosphere. And the atmosphere are the gases that we breathe and the air that we breathe and that sort of stuff. It's different than space, right? And it's different than the Earth. So the atmosphere is all the gases that we need to live, and they are attracted to the Earth by gravity. And so we have an atmosphere that is stuck around the Earth, thankfully. And so that also filters out some frequencies of light when it passes through. That's why in the morning, sometimes you have nice pinks and greens and stuff that show in the sky, because the sunlight, as the sun appears to be just coming up over the horizon in the east, the sunlight, actually, some of it gets kind of reflected and refracted. That means bent a little bit, and so you get to see different colors, and certain things are reflected and filtered out, and that's why the sky is beautiful colors in the morning and evening. Okay, so that's a lunar eclipse. The umbra would be the part of the shadow, and it's in the other diagram as well. The part of the shadow that would be, totally block the sun's light. The umbra, the penumbra, would be, if you were in this region, or if the moon were in this region, it would be just partially blocked. You would have some of the sunlight blocked from one side, but you would still see some of the sunlight from the other. And anyways, that sort of stuff. So I don't think these terms are necessary, but that's generally what a solar eclipse and a lunar eclipse is. You should make sure you label this one solar. I don't see the solar eclipse on here, but when the sun is covered, that's a solar eclipse. Please make sure you have that in your notes. No, actually it is on this little diagram. You might not have it in your notes, but please put the solar eclipse. If the sun is blocked out, it's a solar eclipse. If the moon is blocked out, it's a lunar eclipse. All right, what about the sun? What about the sun? The sun's pretty important to us. It gives us light, gives us energy. It allows plants to grow, to create their own food, and all sorts of things. The sun is very, very important for heat for us and for daylight hours and that sort of thing. The sun is about 150 million kilometers away from Earth. So that's a long drive. That's a little bit further than we would be able to drive without having to go to the bathroom a couple times. It's a long ways away. The sun is a star. Okay, so we look at stars in the night sky, the twinkly, twinkle, twinkle, little star, that sort of thing. The sun is a star. It's our closest star. We revolve around that star. Gravity of the sun holds us into its orbit. So we do revolve around the sun. It's a star is a body of electrically charged gas or plasma that emits energy from nuclear reactions taking place in its core. So that's a little typo there. That should be an E. So electrically, okay, so plasma, you've heard of the word plasma before, electrically charged gas. Okay. A sunspot is a region of the surface of the sun that is slightly cooler than the surrounding regions. So what you would see, and I have some diagrams, but I don't know if I have diagrams. Yeah, the dark spots on the sun like that would be sunspots, I guess. Like they're hot, cold. So the dark spots on the sun, I'll just go back to this diagram here. But if we had the sun, okay, and you would see some black spots on the sun, those would be sunspots, and they're a little bit cooler than the surrounding area. So the sun's like a big mixing pot of hot gas and plasma nuclear reactions and things. And so that's what a sunspot is, okay? Sunspot. 150 million kilometers away from Earth. The sun is a star. It emits energy from nuclear reactions in its core, all this fun stuff. Okay, what is a solar prominence? A solar prominence is a large, low energy, curved, bright stream of particles on the sun. Okay, it appears as a loop on the surface of the sun. Okay, a solar prominence may last for several hours or weeks. So this little loop right here, okay, there's lots going on in the sun. The sun is just a monster. I mean, it's just crazy. But, you know, you have these solar prominences, and we'll talk about solar flares in a second. But solar prominence would be kind of this loop of energy, a stream of particles that seems to explode off the surface, but then gets sucked back in by the gravity and creates this little loop. So you see these things, or scientists see these things through, in their studies. So that's what a solar prominence is. A solar flare would be next. It's a high energy, massive explosion on the surface of the sun. This sudden release of energy often flings hot plasma out into space. So a solar flare is not necessarily a loop like a prominence. So there, in this picture, you would see that there might be a solar prominence here. This might be a little bit of a solar prominence right here. But this would be like a solar flare that doesn't end up coming back to the sun. It shoots out into space. And if this plasma, this radiation reaches Earth, it's our protective magnetic field that protects us from the radiation. So that's where we'll talk about the magnetosphere. We'll talk about the fact that Earth is magnetized and it has an outer magnetic protection from the sun's radiation. Is pretty cool. Well, I mean, if this radiation were to actually penetrate the Earth, yeah, it could cause problems. Yes. Yeah, it's massive. So what is solar wind? So we're talking about solar prominences, solar flares. What is solar wind? Solar wind is a constant flow of particles streaming out of the sun's surface in all directions. It's called a solar wind. Now, this stream of particles in the form of, radiation and different things like that. The northern lights, and they've been in the news here recently. There's been lots of kind of cool northern lights in areas that are further south from the pole than normal. The aurora borealis is the actual technical name for northern lights. They are a result of our magnetosphere interacting and protecting us from harmful solar wind. So let's just zoom in on this little picture here. You fill in your blanks there. Okay. So this little picture here, here's the sun. Okay, a solar flare would be a massive explosion sending energy out, and this is happening all the time. We have little bits of radiation and particles are flying out into space. The Earth, though, here's the Earth. Because our poles, the Earth is specially designed to be magnetic, and what happens is it creates a little bit of a force field around the Earth, and that magnetic force field interacts with the solar radiation, and actually these particles, these electrically charged particles, are attracted to the poles, to the north, the south, so they don't hit straight on the Earth like this, which is really great. It's a bit of a protection here. And then these particles, if they actually get through into our atmosphere, that's when the aurora borealis, or the northern lights, can be seen. And the northern lights, the aurora borealis, are kind of it's almost like a colorful ribbon in the sky, and it's like the particles that are interacting with our atmosphere and kind of lighting up and disintegrating, chemically reacting with oxygen and stuff. And so that's what northern lights are. Maybe I'll grab a snap of northern lights here, but that's how they're created.
God has good problem solving.
Now, you wouldn't see northern lights quite this vivid all the time. As a matter of fact, very rarely would these are special pictures, right? But this is sort of what it would look like. They would have these little ribbons of color. A lot of it's green, mostly green. And why? It's the different particles and different temperatures and the reactions. They're emitting energy, and that energy can meet our eyes as different light colors. And you'll find out more about that in physics and in chemistry when you move up there. But anyways, these are some pictures of northern lights. And of course, in northern Canada, where we are, it's a good place to view northern lights. And of course, if you were in the south, near the South Pole, you would be able to see them there as well. All right. Awesome. Okay, we're just finishing 9.2 here. So these are your textbook questions. You want to copy those down for 9.2 questions to just review what we've been learning here. We will get into 9.3 here today, but these are your questions for 9.2. Now the 9.1 questions do not have to be handed in. They're supposed to be done for today, but they don't have to be handed in. I will collect those questions either at the end of this chapter or at the end of this unit. Okay, so just keep them safe. Don't lose them. I will be giving you some marks for your work, for sure, for that. But let's see, what time is it? That is just 10 o'clock here. Yeah, unfortunately, I think I'll be able to get through 9.3 here as well today, from what I have. Yeah, so we'll be able to do 9.3 as well. We'll take a look at our solar system here today. Okay, guys? Yeah, right now. Yeah. So hopefully you got those questions copied down. Just going to make these a bit bigger here. Well, we're only doing one unit, but we're doing several chapters. Yeah. Okay, so the solar system, 9.3 in your textbook. If you want to turn to 9.3, it's right after 9.2. I don't know exactly what page it is right now. All right, so on page 328 in your text, if you want to follow along here, the solar system is our sun and the planets and other celestial bodies that revolve around it. So when we talk about our solar system, we're not talking about the galaxy, all the stars and stuff that we see. We're talking about just our sort of neighborhood of the galaxy. This is our neighborhood of our big galaxy. And our galaxy is kind of our city in the universe of all the city of galaxies, or of all the world of galaxies. So the solar system involves the sun. That's why it's called solar. That's the word for sun, the solar system. And we have planets and comets and asteroid belts and all this sort of stuff that revolves around the sun. That makes up our solar system. So we have the sun in the middle. It's the largest body in our solar system. That's why all the other smaller things sort of are attracted by gravity towards that. And we are set in orbits, thankfully. Thank the good Lord. And so we have the sun. Then we have Mercury. That is the planet that orbits nearest to the sun. And yeah, it's pretty hot, Mercury. Yeah, you might want to visit there. Venus would be next, then Earth. We are the third rock from the sun, and this is us right here in the Earth. Then we have Mars. You guys know about Mars. You can see Mars in the night sky. And of course, right now, I don't know if you guys know, but you can see Jupiter and Saturn really well in the night sky right now. We have an asteroid belt here as well, then Jupiter and Saturn. And then we have Uranus and Neptune. Now, Pluto has kind of been a planet and kind of not a planet, and it's kind of back and forth. The scientists aren't really sure about Pluto as a planet. I don't think it's on this little diagram here, but Pluto is very small. It's very far away. It takes like 250 years or something to go around the sun once. There's a lot of similarities to the planets that are in our solar system, but there's a lot of differences too. So it's kind of one of those, right now, I don't know. It's kind of like been in and out of the club here eventually. So maybe we could do a little bit more study on Pluto going forward. All right, so here's Earth right now. Notice that there are lots of things that surround or that revolve around the sun in our solar system, not just planets. There are comets. So these are comets over here. Well, black's not going to help. These are comets right here with the tails, and they always face away from the sun. Did you know that? We'll find out a little bit more about comets as we move through this. There's an asteroid belt right here. So that's like a certain distance from the sun. There is this big asteroid belt, which they call it. It's a bunch of rocks that revolve around the sun. They've kind of gathered together a little bit in this thin sort of orbit there. The farther you get away from the sun, the colder things are. That was asked about. So you got hot Mercury and you got cold, Neptune. But yeah, so this is our solar system, and we're going to dig more into that. Now, I did have unfortunately, the internet is not working so well. I did have a little animation showing the sun with all the planets revolving at once. Here, I'll show you that another time. I'll put the link on mrmathwell.com so you can you maybe go to that if you want. But here's Earth, 1, 2, third orbit from the sun there. And I was hoping to play this because, as I mentioned earlier, in the night sky, just at this time of year when we're looking at this here right now, in the night sky, and I'll just kind of maybe draw you a little diagram. So we got the sun in the middle here, if you guys can see that. But we've got Earth on an orbit, kind of something like this, right? So here is Earth right here. That's us. That's Earth. And then we've got Jupiter and Saturn. Okay, so now where's Jupiter and Saturn? So here's Earth. Okay, the next one's Mars, then Asteroid Belt, then Jupiter, then Saturn. So Jupiter's a little bit closer to us than Saturn. So we'll draw another orbit here for Jupiter. Okay, let's move that down a bit. I'm not drawing everything. But Jupiter is, right now, here's the sun. So on this half, on the night half, we're seeing there's a Jupiter right here. And then Saturn. So here's Saturn's orbit, okay, let's say. And in the night sky, you're going to see, here is Saturn right here with its belt. Now, Jupiter is really big, bright, looking like a really bright star in the night sky here. But as we look out, you'll see to your left, you'll see Jupiter, and then just to the right of that, you'll see Saturn. And yeah, I was out there the other night. I was looking at the constellations, trying to find things. And Jupiter and Saturn are two really bright stars in the south sky. So if this is south here, okay, that's south. You're standing and you're looking south. Then Jupiter's going to be right about here, really bright, and then Saturn's going to be right about here, and it's going to be really small and a little bit faint. But if you had a telescope, you would be able to see the rings of Saturn even with a telescope. So I would encourage you, if you have the means, to have a telescope or even, a spotting scope of some sort, you'd be able to look at the moon and you'd be able to look at stars. I would also encourage you to get, if you want to, you can get free apps on your phone that show you in the night sky where the constellations are. And I happen to have one on my phone as well. It's like Skyview Light or something like that. And what I do is I pop it open, and then I just put my phone up to the sky, and you might have to calibrate it so it knows where you're looking exactly. But when you kind of pan across the sky with your phone, it'll show you sort of what the stars are named, where the constellations are. So so right now, if this is my phone, okay, and I'm panning the sky, so these are black. I know these are stars, but if I have this big bright star here and this star over here, on my phone it'll show something. It'll show something like this. It'll say this is Jupiter, and it'll make it's big and animated, and then over here it's Saturn with the rings and stuff, and it's pretty cool. So you can kind of see, and it'll label this as Jupiter and where its orbit is and stuff, and then Saturn. So you can kind of pan across the sky left and right. You can go left and right, and you can see where the planets are, if there are any out that you can see that night, or where the constellations are. And it'll also show you constellations, right? Like here's that big Betelgeuse, and here's Orion's belt, and so on. And it'll show you a picture of Orion on his knees and stuff like this, or with one, his belt here, and then his shield or whatever, his bow, and you've got his hand up here with another knife. So all of these little stars here, right? You'll be able to see that on your phone, and it'll have a little animation of how these stars are forming the constellations. Kind of cool. So I would recommend you looking into that. Maybe you can get some kind of app that'll guide you through the constellations in the night sky. Okay, let's keep moving on. So planets are astronomical bodies, or celestial bodies, you can call them, that orbit stars. So planets orbit stars. Planets have gravity, but they do not radiate. So a planet, this is bad English, sorry. Planets have gravity, but do not radiate their own energy like a star does. So planets have gravity, but they do not radiate their own gravity. You don't have to fix it, but I should fix that for next time. They do not radiate their own energy like a star does. So planets do not emit light. Okay, the sun emits light, stars emit light, planets reflect light from stars. Okay? Planets reflect light from stars. Whoa. Stars in the night sky tend to twinkle, and planets have a steady, constant light. So this is one thing you can, if you see a big star in the sky and you don't know if that's a planet or a star, you kind of look carefully, and stars will twinkle. Okay, stars will twinkle because they're giving off their own light, and it's a constant stream, and that changes as it spans the distance. Planets tend to have a more constant, steady light. They don't twinkle as much. There will obviously be a little bit of twinkle with everything, probably, just given our atmosphere and our eyes and things like that. But that's one of the things you can look at to differentiate planets and stars. Okay, a light year. We talked about a light year, I think, before. A light year is not a span of time. Okay, it's not a span of time. A light year is a distance. It's the distance that light would be able to travel, of course, at the speed of light, in 1 year. So light goes incredibly fast. We're not talking about the speed of light here, but it's part of it. So it's 3.00 times 10 to the 8 meters per second. That's 300 million. Let's see, 1, 2, 3, 4, 5, 6, 7, 8. That's 300 million meters in 1 second. Meters in 1 second. 1 second. So that's pretty fast. I can run not quite that fast. But yeah, so if a beam of light were shot right now, and the beam of light were to go around the Earth, it would actually go all the way around the Earth 7 times in 1 second. So light is super fast. It's almost instantaneous. If we turn the lights on, the light basically gets from the light fixture to our eyes instantaneously. Like we cannot measure the time between when light is turned on, when that light actually gets to our eyes. It's like that. And that's why, and actually sound travels a lot slower than light, so that's why you see things in a distance before you might hear them.
Like a firework?
Like fireworks, stuff like that, you'll see the light burst and then you'll hear the boom. Even in a baseball game. Like I used to play outfield when I was in high school. I played catcher, I played shortstop, I played outfield. But when I was in the outfield, I mean, you'd see the batter swing the bat and hit the ball before you'd hear the crack of the bat, right? So even in baseball that far away, there's a difference between how fast light travels and how fast sound travels. But again, that's in further more in science classes that you're coming up to, maybe next year or the year after. But we'll talk a little bit more about that. Sound travels 332 meters per second. 300 meters per second. This is 300 million meters per second. Million. So that's a lot slower. Okay, approximately 9 trillion kilometers. That's what a light year is. If we're talking about distance, that's what a light year is. Or something like 5.88 trillion miles. So kilometers are smaller than miles, so the same distance would have more kilometers. You guys know that, hopefully. Miles per hour is what our speed in our cars are in sometimes. Kilometers an hour would be more common. In the States and in other parts of the world, they talk about miles, so you'll see both kilometers and miles in a lot of textbooks and things. But just to give you an idea how big our galaxy is, and again, 9 trillion kilometers, 1 light year, that's pretty far. Our galaxy, so that is the collection of billions and billions of stars that make up our galaxy. And here's our sun, somewhere there. You can't even see it, okay, in this picture. You can't even see it. Our solar system is like a speck that cannot even be seen, okay? But the width of our galaxy is estimated to be approximately 100,000 light years. So light would have to take about 100,000 years to get from one end to the other in a one-way direction. Or 100,000 times 9 trillion. Like these are 9 trillion kilometers. These are numbers that are not even fathomable. So it is absolutely incredible just how wide the vastness of space is. Billions and billions and billions, hundreds of billions of stars in a galaxy, okay? Millions of light years between galaxies, billions and billions of galaxies in our universe. Like it's unfathomable. It's absolutely incredible. And we are a small speck in a small speck in the large ocean here of the universe. Pretty cool, pretty humbling. So our Milky Way galaxy, approximately 100,000 light years across, Okay, so you would, if you were going to drive that in your car, you would definitely have to stop a few times to go to the bathroom, for sure. Okay, right on. And if your car was going the speed of light, you'd be in big trouble anyways. You wouldn't age, but that's another day. Wait, what? You wouldn't age? What? Oh my goodness. Okay. Oh, sorry. Theory of relativity. Just look up Einstein theory of relativity. You can let that lull you to sleep tonight if you wish.
Is that E equals MC squared?
E equals MC squared. Yeah, that's Einstein. Yeah. Okay. Yeah, I know I've opened a can of worms there. Sorry. Let's continue on with the subject at hand here, of course. Rocky planets. Rocky planets. Now, these are the planets that have really lively music, lots of electric guitars and things. No one got that joke? Okay, fine. Rocky, yeah, thank you for the laughter, totally unsolicited, totally natural. Thank you. In our solar system, some planets are made of rock material, and some are made of gas, lots of gas. Mercury, Venus, Earth, and Mars are made of rock. Jupiter, Saturn, Uranus, Neptune, made of gas. Question?
I have to go for piano.
Really? Okay. Sorry, did you say you had gas?
What? No, I have to go for piano.
Oh, you have to go for piano. Oh, okay. Okay. So I was waiting for that. Okay. Who in here is made of gas? No, I'm just kidding. Okay. Okay, I don't know how many of you are wearing an asteroid belt here today. Anyone? I have an asteroid belt on. It's actually not true. Mine's leather. But an asteroid belt between the inner rocky planets and the outer gas giants lies a huge band of billions of rocks circling the sun. If we go back to our little picture here, there's the...
Is that a real laugh?
The rocks in the belt can be the size of pebbles or up to 1,000 kilometers wide. 1,000 kilometers wide. 1,000 kilometers. Okay, so that's driving about 10 hours. So that'll be from here to somewhere, here to the mountains or so, to the Rocky Mountains from middle of Saskatchewan where we are. So that's pretty big. Yeah, that's pretty big. To have a rock that big? Yeah. That hits the Earth, we're done. Okay. Asteroid belt. Comets and meteoroids. What are these? Comets. Let's talk about comets. A comet is a celestial object made of rock and ice. It's like a dirty snowball. So if you were to go out to the street here in the middle of winter and you were to make a snowball from the snow that's in the middle of the street, you would get some snow, you would get some rock, and you get some dirt.
What do you mean? It's just throwing ice balls.
Exactly.
And rocks.
Comets orbit the sun like planets do. So comets orbit the sun like planets do. Halley's Comet, that looks like Halley's, it's Halley's, pronounced Halley's. Halley's Comet orbits the sun every 76 years. Now there's a whole story behind Halley's Comet. You can look this up another time. But it was named after Edmund Halley, I think years after he died, but he had predicted that this was going to come back and blah, blah, blah. He did a lot of work on this, and he figured out it's a comet, it's orbiting around the sun, but it's different than our planets and stuff like that, but it's definitely coming back. So in 1986, I was alive then. I was actually about 12 years old then. And in 1986, I saw it with my own eyes. It was close enough to the Earth to be seen. So I'm going to blow up this little diagram here. Okay? So here's the sun in the middle, little sun in the middle. Earth's orbit is also right near the sun there. And here's the comet's orbit. So it's coming like this. So 1977, it was kind of between Uranus and Neptune's orbit. And then in 1985, it was just inside Saturn's orbit and so on. And it kind of slingshots around the sun. It kind of gets drawn towards the sun. And then it kind of comes around and gets slung back out into space. So this is the orbit. It's really elliptical. It's kind of really kind of flat. Comes pretty close to the sun. So in 1985, it was here. And 87 was here. So 86, it was right here close to the Earth's orbit, and we could see it in the sky. It was mostly just kind of like a fuzzy ball of light. If you looked in a microscope, if you looked in a telescope or something like that, you could definitely see the big long tail behind it. It was kind of cool. I don't remember much of it, but I did see it when it was there in 86. Now it should. So what's 86 plus 76? 150, 160. 62. So 2062, you guys will see it. Hopefully. Probably. You're not going to be dead in 2062. You're going to be dead in 2062. You're going to be like 50 or something, you guys.
Actually,
What will happen?
Come on, dead. Anyways, you'll probably see Halley's Comet when it comes back.
Destroyed?
Well, who knows? The Earth might be over by then, but
Yeah, that's what I'm saying.
if the Earth is still around, you guys will probably still be alive. Okay, try and make it to 50 or so. It's good. Yeah, hi.
what would it be right now for 2021? What would it be right now?
Well, okay. Okay, so it's okay, guys, it's not. It comes around, it's going to be seen predictably about every 70, girls, about every 76 years, okay? So that was, let's see, 86 then, 32 years ago, I guess. So where is it right now? Well, this is where it says here in 2006, around here. It's probably it's probably the furthest away from us that it could possibly be. It's going to be right near the end here because 32 years ago it was here, so that's not quite half of 76. So it'll be somewhere around here probably. This is where it is probably right about now. So it's got a ways to go. It's not on its way back to the sun yet. Wouldn't be on its way back to the sun yet probably. It's still on vacation. It's still heading out. Yeah, it's not coming back anytime soon. Another 40-some years. Yeah, it probably won't kill us all. I don't think.
It's
No.
powering up so it can
Yeah, I don't think so. Okay, guys, one last slide here. One last slide before we really finish off chapter 9. So let's get this in here. Meteors and meteorites. Okay, so you've heard of meteors, you've heard of meteoroids, you've heard of meteorites. There's a difference between all those terms. So let's learn about that. A meteoroid is a small piece of rock that travels through the solar system with no prescribed path. So it's not part of the asteroid belt that has a prescribed path. It's just a piece of rock that is flying around space. Okay, that's called a meteoroid. It could be large, small, whatever. A meteor is a meteoroid that collides with Earth's atmosphere. So let's say we have this little piece of rock, and it actually collides and gets pulled in by the Earth's gravity and collides with the Earth's atmosphere. It's coming down to Earth. That's a meteor. So basically, it's a meteor while it's in the sky. Okay, while it's in our atmosphere. It's a meteoroid out in space. It's a meteor when it hits the atmosphere. It collides with Earth's atmosphere and starts to burn up because of the friction with the air. So, I mean, if you guys are driving in a car, don't do this, but if you're driving in a car and you hold your hand out or you hold your face out or something, the window while you're driving down there, you're getting a lot of wind, and if you hold it out long enough, it'll actually feel like you'll get some wind burn, like it'll start to feel a little hot. Well, imagine that. Imagine going thousands of times faster than that through the air. Your hand would literally burn up. That's what's happening with these little rocks that fly through the air. They're plowing through all the air molecules, and there's friction, and it starts to burn up. Okay, so most meteors completely burn up, and as mentioned before, shooting stars are not actually shooting stars. They are meteors that are burning up in our atmosphere. So it's a piece of rock from space. It's drug in by our Earth's gravity. It hits the Earth's atmosphere. As it falls to the Earth, it starts to burn up. Now, if it doesn't completely burn up, the meteorite is the fragment that makes it to the Earth's surface. So, meteoroid out in space. A meteor, when it's a falling star, is a meteor. It's not a star at all. And then if it doesn't burn up completely, and there's a piece of that rock that hits the ground, and it stays as a rock in the ground, doesn't burn up into nothing, then it's called a meteorite. That's a fragment. So I'll show you some pictures of meteorites, and you can probably look that up yourself as well. But I'll maybe grab you a picture, video here. But there are meteorites that are found on the Earth, and you know what? These are space rocks that actually made it through the furnace that is our atmosphere and actually hit the ground. So kind of cool. And of course, scientists do all sorts of studies on those to see what they're made of and what they can learn from space. Okay, so on page 337, we talked about Pluto.